Hello, everyone. Thanks for joining the webinar. I am Gilberto. Before starting, let me say that the webinar is being recorded, and at the end, we're going to send the recording link to everyone that was registered to the webinar. And second, during all the time of the webinar, you can write any questions you have on the Q&A box, the question and answers box, and we are going to answer at the end of the webinar. So let me start. So I am Gilberto Braia. I am the head of sales here at Move Solutions. I am here with Andy Beardsley from Terra Measurement, which is one of the technical partners of Move Solutions in the UK. So let me start, for who doesn't know it, a brief introduction about the company. So we are Move Solutions. It is a company developing smart structural health monitoring systems in the world of structures and infrastructures. So we're basically working worldwide, realizing a new generation of technology about sensing and let's say wireless monitoring of every kind of structure and infrastructure. So in the world of the Internet of Things. So talking about the industries and the applications, we work on, let's say, different industries. So we work on construction sites and building. We work on, let's say, construction sites, buildings, and monuments. We work on bridges and overpasses and viaducts. We work in the railway applications. I mean, everything about the railway and the environment around it. And we work on infrastructure like dams, tunnels, roads, and whatever. So today we're going to focus on the railway monitoring applications, not especially about, about the railway track monitoring, but on the embankments. I mean, on the even the environment which holds the railway itself. So talking about solutions and, let's say, the technology that we can provide. So in the railway environment, there are several parameters that we can measure and monitor. So let's imagine a railway track that has around, I mean, first you can measure the geometry of the track itself, but you can check, of course, the ground and the water. You can check every kind of infrastructure, like the tunnels which the railway passes through, bridges, and meteorological parameters like wind and rain and temperature. So you can see that basically you can check everything with a single system, which is pretty complicated. Today, we're going to focus on embankments. So what's an embankment? So it is basically the backbone of a railway track. So it is usually made of ground, rock, and other materials, and it holds the railway itself. So it's something that really needs to be checked, to be monitored, and to take care about, because it holds the railway, which holds the train itself. So it's something really important. And since it's made of dirt, of ground, it ages a lot, and it's subject to heavy rain, wind, and other let's say strengths that made it age a lot. So it's something really important to be checked. So what has been done until now with the traditional technology? So first thing that it's possible to do, and it's always been done over the year, is to use total stations. So what's a total station? It's basically an instrument that is placed on a spot that it's assumed to be still, and with some points, with some targets, you can measure several points, in this case on the railway or along the embankment, to see how all these points move respect to the point of installation on the total station itself. So you can check this kind of movement. Total stations can be manual or robotic, and you can and basically it's a classical way to do a monitoring. Of course, it's effective and it works pretty well, and sometimes it's necessary, but we are now presenting something different that is a lot easier to install and manage, and basically has very lower requirements to be installed. So this is one of the classical way to perform the monitoring, but exactly, it's expensive and complex. Other way is basically the tilt meter chain. This is for the ground. So you can basically drill the ground and insert a chain made on several tilt meters, one connected to the other. That is something very useful sometimes when you have to go very deep to understand how the ground is changing its shape along its depth. But of course, even this kind of installation is very invasive and long to do. So we're again proposing something different. So what can we provide? So you understand that on a railway sometimes you have some accessibility issues, because you mean maybe it's in the woods under the rain, or railways are everywhere, right? So we developed a system that is based on very easy to install devices. So they are boxes like this one that are made of basically the sensor itself, the power for the sensor, and the transmission of the data. So basically, they are closed boxes, super easy to install. They're provided powered, and so no need of doing any kind of setup in place, any kind of power the sensor in place. So they are very easy to install. The battery, we work with a low power wide area network, which has a very low power consumption. So it's very easy to have batteries, onboard batteries that last for years, several years. So how's the system? So you basically place different sensors on an area that can be sensor of the same type, of different kinds, doesn't matter, several sensors. All of those sensors communicates to a gateway, which is a central unit that receives all the data from the sensors, and the gateway then uploads everything to the cloud. On the cloud, you have a platform, and that's there that you can set up the sensor remotely from your home or your office. You can check real-time data. You can combine more measures to get, let's say, a more advanced information from more sensors. So that's what we provide, which is really fast to install and manage, and everything is smart and remoted. So you have then a platform that is web-based. You can access it from everywhere, where you can use it during the installation just to check that everything is working and the sensors are successfully connected to the gateway. And then you can use it, of course, to do analysis about your monitoring structure or environment or infrastructure. So that's it. In the case on the embankments, what we made, what Terra Measurement made is basically setting up a grid of several tilt meters, smart tilt meters, mounted on a pole that was then installed on the ground itself to understand how this grid is changing its shape over time. But I'm happy, let's say, to let Andy explain it better, since he is basically the company that performed this kind of monitoring. So I leave floor to him. Thanks.
Thanks, Gilby. I will just get my screen share. Just bear with me.
Sure.
There we go. So hopefully everybody can see the first slide. So yeah, thanks to Gilby, and hello to everyone around the world attending today or watching the webinar later, of course. I'm pleased to introduce you to the benefits of structural health monitoring for slopes across the UK rail network. So I'm Andy Beardsley, I'm the MD of Terra Measurement Limited, and I have been a geospatial surveyor and consultant for 32 years. Terra Measurement are expert geospatial surveyors and consult and work across many sectors and environments. We work for a wide variety of clients across those sectors, and some of our biggest clients are in the rail sector. We use our expertise along with advanced equipment, methods, and software to provide 3D geospatial surveys, 3D monitoring, remote sensing, structural health monitoring, and solve many problems with accurate 3D geospatial data. We don't only specialize in collecting good data in the field, but also in ensuring that clients and project stakeholders can view and use our data easily and effectively, as well as the drawings and models we produce. In the case of structural health monitoring, the Move Solutions Cloud Platform is a key element that enables us to bring many different types of monitoring data into one place, all in an easy to digest graphical form. So the other logo that you can see on the slide, we're also, as Gilby mentioned, technical partners of Move Solutions, alongside our good friends and fellow collaborators, Academy Geomatics and Encompass Surveys. The technical partners alongside Move Solutions are unique in the marketplace, really. Unlike other SHM equipment and system offerings, we're available for consulting, frontline services and installation, but most importantly, ongoing support and reporting, all with the backing of the Move Solutions team. So let's look at the UK-wide rail network challenge of slope stability and safety. Following the tragic train derailment at Carmont on the 12th of August 2020, Network Rail appointed a task force to undertake a review of their management of earthworks. At the same time, the Weather Advisory Task Force, chaired by Dame Julia Slingo, was also appointed. The Network Rail Earthworks Review final report was produced in March 2021. The report mentions at least 32 major slope failure incidents in the preceding 15 years. Unfortunately, there were many more incidents in that time period. Some of those and more recent examples are on the carousel of this slide as I'm talking now. To give a clear vision of the scale of the potential problem, I need to mention a few facts. The UK rail network has 20,000 miles of track. Across that area, Network Rail manage a portfolio of over 190,000 earthwork assets, most of which were built over 150 years ago. These assets comprise of 100,000 embankments, obviously of various lengths, 70,000 soil cuttings, and 20,000 rock cuttings. So just to be clear, an embankment is a construction that allows railway lines to pass at an acceptable level and gradient over low-lying ground. A soil cutting is an excavation that allows railway lines to pass at an acceptable level and gradient through the surrounding ground that is comprised entirely or predominantly of soil. Excuse me. Rock cuttings are an excavation that allows railway lines to pass at an acceptable level and gradient through the surrounding ground that is composed entirely or predominantly of rock. So why do we need a better reactive response, never mind trying to achieve a proactive response? Most of our infrastructure slopes are more than 150 years old and do not offer comparable levels of capability and resilience to modern engineered slopes. They have been relentlessly subjected to gravity, weather, seasons, and traffic impact, all alongside their individual construction or geological quirks or flaws. Then we have the problem of managing the impact of extreme weather and climate change on these assets. Network Rail spent 38.6 million repairing damage to its network caused by landslips last year alone. So on top of the earthwork assets, there's also a resource problem for Network Rail as well. And a new civil engineer reported that there are 500 built structures that have not been inspected for over 5 years. And built structural monitoring is another subject in itself, even just within the rail network. I'm supposed to be pressing the carousel, so I'll now click through some of these sites. So the most recent landslip is at Aycliffe, which I'm sure you all saw on BBC News. So let's play on the video. There are many geospatial survey methods for monitoring slopes, and these are often requested in slope-related Network Rail project requests. The basic geospatial methods involve installation of wooden pegs or markers across a slope area, then measuring a 3D or 1D position with total station or digital level, then repeating the measurements for a comparison at nominal time intervals. Here are some of the major challenges to these methods. As you can see in this video, vegetation. If an embankment isn't covered in trees, it is covered in bushes and brambles. And if it's not covered in either of those, there will be tall seasonal vegetation instead. Only on some rock cuttings or slopes after significant civil engineering is there no vegetation at all. Why is this a problem? Because all accurate geospatial surveying needs clear line of sight to all of the survey control and monitoring points required. And although devegetation can take place, in some circumstances it is both expensive and can paradoxically cause further slope instability once the root system has died away. Survey control. At this site on the screen at the moment, it was completely impossible to install survey control. And monitoring of high accuracy the survey control must be positioned outside an area of influence that might be affected by slope movement or subsidence. The installation and method must be repeatable so that any differences in the data is due to movement, not survey inaccuracies. And then finally, safety. With the constant need to focus on health and safety, a robust safe system for working on a significant slope must include IRATA rope access systems. Therefore, this IRATA access is required not only for the installation process, but also for every single manual monitoring measurement visit thereafter. So, to move on to some of the disadvantages of geospatial monitoring of rail slopes. Once the baseline coordinates or levels are recorded, there is only a monitoring comparison when there is a revisit. That might be weekly, monthly, quarterly, etc. This means collapse, trends, fluctuations, or weather-related events are completely missed. Data comparison is usually a manual spreadsheet exercise and not easy to interpret. This, compounded by the large time frame between measurement visits, make an exercise that is basically ineffective in most cases. In many situations, both installation and remeasure need nighttime track access, IRATA staff, safety staff, etc., causing a large total budget cost. Third-party land access can often be required to get the survey control outside of the area of slope stability influence, and that can be the challenging problem, even if it is possible. Wooden pegs or markers may be unstable immediately after installation. Repeated devegetation may be required, as lines of sight are often affected by seasonal vegetation growth. And then finally, extreme weather can affect the accuracy of traditional monitoring or even cancel shifts due to wet survey equipment. So this is a summary of how our SHM, structural health monitoring, slope monitoring system works. The planning stage includes designing the monitoring layout on the basis of track fault locations, other information provided, and meetings with the local Network Rail Structures team. The method of power system for the transmission gateway is also established on the basis of what's possible. A safe system of work is created, including IRATA rope access planning, possessions, if required, light devegetation, or urgent slope remediation. As you can see on this video playing at the moment, this is the extreme weather that would have rendered a geospatial installation impossible. We would have to cancel the shifts. So after a cable and services clearance survey, pole-mounted triaxial wireless tilt sensors are positioned at the top, middle and bottom of the slope as a minimum. Where there is a known track fault or influenced area, the sensors are placed at approximately 5-meter lateral intervals, top, middle and bottom. In between these areas, they are positioned at approximately 20-meter lateral intervals or greater. In the 5-meter positioned area, if any sensor is in an area of sudden subsidence, the surrounding sensors will show the size and impact of that subsidence. In the very unlikely event that a sensor will slip but stay vertical, the sensors surrounding it will be pulled and pushed and show that the event has happened anyway. For all slope projects, the situation is monitored alongside threshold exceeded alarms. This is the fastest method of an asset engineer being notified to stop train movement if a landslip is suspected. Longer-term installations show the trend over time and inform the cost analysis of either continued monitoring or civils remediation. The most effective solution to slower embankment movement is to see the trend over a year through all seasons, temperature, weather conditions, and ground saturation. So what's really good is that the system can be set up anywhere on the network, as the data transmission gateway can be powered by either an off-grid power system or a power bank supply, all housed in a secure cabinet. Other types of sensors, including geotechnical, environmental, structural, and video monitoring, can be added to the system at any time to help provide the ideal assessment. So, once the system has been installed, the sensors are calibrated remotely and the measurement interval set. The measurement interval is usually set to 2 minutes. At this point, I must emphasize 3 major differentiators between traditional geospatial monitoring of slopes and our system. So number 1, our system is providing a high frequency of readings, which is angle and temperature, every 2 minutes from the moment of calibration, or within an integrated cloud-based software platform with data analysis tools and comparison. The traditional methods only provide readings with a large time frame in between, basically after every visit and then when the data is processed. And as I mentioned previously, that data is also usually shown on a spreadsheet, which doesn't provide anything other than slow manual analysis and interpretation. Point number 2, after the SHM system is installed, all readings are being received without any further expensive site visits involving possessions, staff, IRATA rope access, third-party land access, and so on. Number 3, there is a subsidence alarm system at the site detecting at 2-minute intervals for the worst case scenario of track damaging landslip. This solution is provided with the concept of the Internet of Things. In this case, it is comprised of wireless LoRa and tilt sensors and the data gateway on site, rapid data transmission to the server system, and then rapid deployment to the cloud-based software platform. The advantages of high-frequency data and analysis, the subsidence alarm system, the significant reduction of site visits make for a very cost-effective system that can inform network rail asset teams better than ever before. In the Network Rail Earthworks Review, it is recognised that extreme weather events are causing increased pressure and negative effect to our rail network slope assets. Here is an example of a weather event at one of our sites, Storm Babbitt. Storm Babbitt raged across the UK from the 18th to the 21st of October 2023. In the region of this project, over 100 millimetres of rain fell, most of it in just around 24 hours. In parts of eastern Scotland, there was a dramatic 150 to 200 millimetres of rain in that same period. Although this is only a screenshot for the purpose of this webinar, it is easy to see the tangible effect of Storm Babbitt on this embankment at the position shown in the overlay tool. In simple terms, the trends before and after this storm show that some of parts of the embankment have been permanently affected. The angular accuracy of the sensors is down to 6 decimal places. Some of the sensors varied only 0.1 of a degree, plus or minus 0.1 of a degree, for the 3 months leading up to Storm Babbitt. Then suddenly lurched forward 0.6 of a degree in the 2 days of Storm Babbitt and stayed there. So basically, what's happened since I took this screenshot is that, and they have remained on that trend. So there has been a change, although it wasn't a slip. So I speculate there actually could have been hundreds of miles of embankment damage from Storm Babbitt alone, but it's yet to be discovered. And the point is, it hasn't slipped yet, but was it affected by it? So the next two slides give a simple overview of two network rail slope monitoring projects. These sites were completed with our client of over 10 years, QTS Group. Their proactive approach to proven innovation and our collaborative relationship led to both of these projects being smoothly executed, which was a pleasure. Always is a pleasure to work with them. So at this site, there are 220 metres of densely overgrown and wooded embankment to monitor. Minimal light vegetation only was undertaken to facilitate the installation. There was one known track fault, but other instability evidence was observed along that 220 metres. There are 36 triaxial tilts installed, 24 clustered around the track fault location, and the remainder spread along the project area. The gateway is powered by a 3-battery power bank that lasts for approximately 3 months, and the voltage is monitored remotely. When the voltage reaches the low threshold, the batteries are swapped in a simple exercise that does not require site safety staff, because you can see in that middle right image, the access gate is there and there's the cabinet. So although the batteries are heavy, it's a very quick swap. The project will analyse trends over several seasons to help assess the need for civils work intervention. The installation took 2 days, with 3 days overlapping facilitation from QTS in terms of devegetation, and just there were some remedial works that needs to be done as well. The sensors can be dismantled and redeployed on future network rail projects, a huge sustainability message and cost-effective message. So project example number 2, 250 metres of variably overgrown and wooded embankment to monitor. Minimal light devegetation was undertaken, not mass devegetation. On the top left image, you'll see that there was a tree removed, but that was removed because it was deemed to potentially be affecting or causing the track fault. There were 3 known track faults. There were 54 triaxial tilts installed, 34 clustered around the track fault locations, and 18 spread along the remaining project area. The gateway was powered by an off-grid power system, with both solar panel and wind turbine charging the power bank. Palisade fencing was installed around the off-grid power system that you can see in that video on the bottom left, just to add extra security. The project analysed trends over several seasons to help assess the need for civils work intervention. As shown in the earlier video, the rainfall was extreme through most of the 3 days of installation, and that would have rendered the geospatial survey originally requested impossible during those conditions. Again, sustainability. The sensors have been dismantled and are to be redeployed on another imminent embankment project. So they've been demobilised, checked, and ready to go out again. So it is extremely cost effective. So just to give a quick broader picture, the slope monitoring and alarm system mentioned in this webinar is just one solution, but there are many other applications and sensors that can be used to monitor many other assets or situations in a rail network. So currently, between us and the technical partners, we've got lots of rail projects out there, and some of them include tunnels, retaining walls, culverts, culvert head walls, bridges, and obviously slopes. The New Solutions Cloud platform does not only display data and provides tools for their own sensors, but also for many other sensors. These sensors include environmental, weather, geotechnical, etc., all contributing to an almost open source approach to solving a project's monitoring needs. There is also track-based innovation that is available now, and we are currently in the process of gaining network rail approval for track-specific applications that will unlock the Move Solutions rail tools and analysis innovations within the cloud platform. These include vertical deflection, cant, twist, and ballast void detection. Further innovation developments for 2024 make for a very exciting time for those of us that love to efficiently solve problems, collect, display, and share useful data. Some people might call that geeks, but we love data. My mouse had disappeared there. So, to draw some conclusions. As we've explored today, the stability and safety of slopes within the UK's rail network presents a significant challenge, especially in the face of extreme weather events and the age of the rail infrastructure. As shown by Network Rail's Earthworks Management Report, there is a crisis emerging in our rail network, as many that work within the rail network are already aware of. Repairs are costing between 30 to 50 million pounds a year for landslips alone. It's extremely reactive when actually there's probably preventative maintenance that could be implemented if there was more of these systems deployed out on the network. What's worse is the potential risk to rail passengers. Let's just say it. Our work at Terra Measurement, in collaboration with Move Solutions and our technical partners, represents a paradigm shift in addressing these challenges. Our structural health monitoring (SHM) system, alongside our advanced geospatial survey methods and the Move Solutions cloud platform, is not just a technological innovation, it's a proactive approach towards ensuring rail safety and reducing the risk of slope failures. As we've seen from the example of Storm Babbitt, and we've got lots of other real-world scenarios, our system's ability to provide high-frequency, real-time data is crucial for timely decision-making and emergency response. Moreover, our approach significantly reduces the need for costly and hazardous site visits, leveraging the Internet of Things and remote monitoring to deliver a more efficient, cost-effective solution. It's not just about data collection, it's about integrating and interpreting data to make our rail network safer and more resilient. In conclusion, the future of rail safety and infrastructure management is here. With the continuous evolution of our technology and the dedication of our team and partners, we are committed to enhancing the stability of the UK rail network, protecting its users, and preserving its vital role in our national infrastructure. So I'll leave you with this quote that came to mind when thinking about how the UK's future prosperity depends on having an efficient, sustainable and well-maintained railway system. We cannot solve our problems with the same thinking we use when creating them. And in the background, there's an image of a hand-built railway network, which is basically what the UK is running its trains on. So I hope you found this interesting, and thank you for watching.
Thank you very much, Andy. I think it was a very good presentation, very clear about all the applications. So thank you very much. And I like the Einstein quote at the end, so I really liked it. So Andy from Terra has been one of our technical partners there in UK. For a while right now. We're doing some great projects with them, so we're very happy to cooperate with him, like with the other partners. So thank you again. Now I can share my screen again with some contacts, and then I can answer some question. Just a second. Okay. Yes. So these are my contacts. You had also the Andy's contacts in the screen before. And you can ask even to me if you missed them. So for any contacts, any questions, even in the future, no problems. So let me and Andy answer some questions that we may have got. Just a second, I pick them, if I find them. So, okay. So I have a question. This is for you, Andy, if you know it. So how deeply might the tilt meters be installed with a drill? So
Just say that again, Gilby.
How deep you can drill the tilt meters on the ground, and how deep do you think it? Let me add. How deep do you think it makes sense to do that?
So the tilt meter itself is mounted above the surface. I don't know if you remember seeing the images that both Gilby and I shared in the presentation. So the whole idea is we're not looking for subsurface movement. That's where an inclinometer, just as Gilby stated, you might have a digital inclinometer that goes very deep down into an embankment or a slope. This is talking about surface land, the near surface landslip capability. So what we're doing is we're installing a post approximately 1 meter to 1.5 meters into the ground, if the ground is capable of taking it that way. So So we mount it other ways in rock environments and so on. We might adhere it to rock faces or whatever. But in an earthwork embankment, it's positioned to detect the kind of near surface movement, and also obviously if material is coming from somewhere else, it will still push over the tilt and show that detection. So we're not only sometimes we're not only detecting where the tilt is installed, but we're also detecting if that tilt is being affected by debris coming from somewhere else as well. So the depth is approximately 1 meter to 2 meters maximum.
Exactly. So this was a case. Let me add that sometimes it can be it can have totally sense to, like, let's say, use in-ground deep tilt meters, like the tilt meter chain that I showed you in my first slides. So this was just not the case because Terra decided to perform a different kind of monitoring. But talking about, let's say, the in-depth tilt meters, you can go down also some tens of meters, and even more, connecting more tilt meters one to the other. That's something that we can provide anyway. So another question is this is for me. Have network rails started to roll out this cost-effective safety and assessment solution in any regions? So I think Andy showed something already. So let me say that what we installed around network rail infrastructure, that's something that we have done with our partners and customers in UK, is being accepted and allowed from network rail, but everything has been, let's say, on the environment, on the, let's say, structures around the truck itself. To install on the truck itself, it's required an approval, which we are, let's say, which we have requested. So we are stepping the path to get the approval and install on the railway track itself. That is something that we are doing already in other regions around the world.
Can I answer that one as well, Gilby? Because
Sure.
in the slope context, it to answer that question literally, so have Network Rail started to roll out this cost-effective safety assessment and solution? No, they haven't really. What it is, it's a few projects here and there, and what there seems to be a bit of a disconnect between the sort of higher level strategy decision makers within Network Rail and the frontline structures leads that actually are desperate with minimal resources to actually understand what's going on in their region. So we're trying to do webinars like this to raise awareness that it is cost effective, accessible, and sustainable to be looking after these slope assets that could cause a danger to passengers, never mind cause expensive repairs once a collapse has happened, and they are happening regularly. So it's not yet, but let's hope that people are starting to listen, that these things can be done.
Exactly. Thank you, Andy. We have some more questions. So, of course, for the ones who are asking for receiving presentations and everything, what I ask you guys is to text me on my email, which was on the slide before, gilberto.braglia@movesolutions.it. I am sending you both the presentations if you want, and also some other materials that you may require. So no problems for that. So other questions. So what is the maximum distance between different sensors and between sensor and gateway? So there is not maximum distance between different sensors because our network is not a mesh network. So basically sensors are, let's say, they are not connected each other, but it is a star network, which every sensor talks directly to the gateway. So on the distance on the gateway, let me say in an average situation, in an average application, you're around, let's say up to 1 kilometer around the gateway. It depends. Of course, we are in the telecommunications, so it depends on the environment. If you are along a railway without obstacles, you can go even higher. If you are like underground or in a heavy urban application, maybe you have to stay in 500 meters around the gateway. It depends. What is really important is to install very well the gateway, because it's the thing that gives you the coverage. So maybe installing on a pole in the right position. This is like a key parameter to take care about. Someone is asking me about new releases. So for now it's secret, but send me an email and we can talk about what let's say what you need and what we are working at. But text me a message through my email. That is the best way.
There are lots and lots of good secrets. So yeah, we're excited about the future of Move, and I'm sure Gilby is too.
Yeah. Yes. Uh, do you still hear me, Andy? Okay, I lost my connection. I lost my connection for a second. Oh, yeah. So not talking about new releases, since for now it's still a secret. But text me. Uh, Another question. Yeah, so sorry if I missed. Are we talking about specific brand of tilt meters? Yes. So this webinar is hosted by Move Solutions, which is a developer and manufacturer of specific structural health monitoring, smart sensors and systems. So we're talking about our, let's say, Move Solutions tilt meters and Move Solution systems.
The key differentiator is the not only the sensors, but the Move Solutions cloud platform. The huge differentiator is how well it brings all of this information in. So yes, the Move sensors, but the cloud platform also allows other information from other sensors into that. So you've got a project with all kinds of information, geoenvironmental, crack gauges, strain gauges, inclinometers, piezometers, water level, all kinds of information that feed into a very quick way to appraise complex information in a graphical form. So it really is a solution. It's not about just a box or which brand it is. It's the rounded solution that is the big reason to use it.
Yeah, totally. I mean, so this webinar was focused on embankments applications. So we definitely focused on tilt meters and, let's say, environmental sensors. But in our system, we have several kinds of sensors. We definitely approach wireless dynamic monitoring. This is something really interesting. So what I may suggest is to contact us to have more information, even about, let's say, about the whole system. And even if you want more documentation, you can go on our website and looking at the other webinars, looking at all the presentation, and of course, just contact us. Okay, I think we answered to all the questions, Andy.
Yeah.
So, yep, I'm just having a final look to see if I missed something. Okay, we're all set. We're all set. Okay, perfect. So let me say first, thank you, Andy, for the beautiful presentation, for your explanation. It was perfect, and joining us. And thank you, everyone, for joining the meeting, joining the webinar, and hope to talk to you if you're interested very soon. Thank you very much, and have a good day, everyone.
Thank you, everybody. Bye-bye.
Ciao, Andy.